We have seen these slides earlier. This one tells the difference between the combinational logic and the sequential logic. And we mentioned about the key differences. In sequential circuit, there's a memory unit, which stores the current contents of the system. And this current content of the system will come back here, affect the combinational logic, which is going to eventually impact the output. So the output is not only depends on the input, it also depends on the memory unit. So before we talk about how to specify and how to design sequential systems, the first thing we need to answer is, so how do we store the memory unit? So the basic memory unit is called a latch, which has two outputs, a Q and a Q prime, which are always complement to each other. And depends on what kind of latches you are using, there are different ways to fit the latches. And here is a small example of a NOR gate for latch. So what we have here is we have an input R and S stands for set and reset. And these are the two outputs, Q and Q complements. And in the middle, there are two NOR gates, and then they are cross-coupled. So let's see, what happens with this circuit. So if I set S to be 0 and R to be, if I set S to be 1 and R to be 0, and this one is going to produce output 0 for gate 2. And then this 0 will come back here, so now I have two zeros to NOR gate number 1, and then it will produce output 1. And this 1 comes back, and then two 1s make this NOR gate a constant 0. So what we see here is the circuit becomes stable. And then we have Q equal to 1 and Q prime equal to 0, complement to each other. So now what do I do is, now let's assume that I change the signal of S to 0. So instantaneously, this 0 is going to change. So this 0 and the 1 here makes this one still a 0, because I have a 1 here. 1 and 0 make this NOR gate a 0. So because this 0 doesn't change, for this gate, nothing is changed. 0 is here, and then 0 coming back, making you a 1. So that means if I change this to a 0, the system status doesn't change. Okay? And you can analyze, once we further change this to a 1, now the things will be different. Because this 1 will change this to a 0, and then this 0 will make these two zeros, change this one back to a 1. And then this one coming back, make this one a stable 0, so the system will flip. The Q changes from 1 to 0. And then Q prime changes from 0 to 1. So what we have seen here is, so the output of this latch, Q and Q prime, depends on R and S. And however, it can become stabilized. Can store a value here, either 1 or 0. And one problem about this latch is the output changes as soon as the input changes. So this is what we call asynchronous system, and which may not be what we prefer. So the flip-flops is a solution to solve this problem. It is very similar to a latch, but however, it has a signal to control when the output can change. So this is the RS flip-flop implemented using 4 NAND gates. And we're not going to go through details about how this one is implemented. We'll just show you the logical diagram for RS flip-flop. So what you see here is we have 3 inputs, S, R, which we call the flip-flop input function. And there's this signal, which is normally we call the clock pulse. This is the clock signal. And for these systems, we want to make sure that at least one of the input R and S will be 0. We don't want to do set and reset at the same time. Otherwise, the system becomes unstable. And the systems have 2 outputs, Q and Q prime, which are supposed to be complement to each other all the time. And what will be the memory content? We assume that currently it has Q of t. And at time Q of t plus 1, what will this memory be? It depends on the input as an R and also the current memory content, following this formula here, S plus R prime times Q of T. And when we design sequential systems, we want to know that how we can give flip-flop input functions values such that the flip-flop will change as we want. So for example, consider this SR flip-flop. Let's see, we want to change the Q from 0 to 1. How can we make that happen? So this table, which is called the excitation table, tells you how you can make that happen. As soon as you set S equal to 1 and R equal to 0, you are going to set the flip-flop. So next time, the flip-flop will have a 1. And for another example, if you want the system to stay at 1, 1, no change, what you do is you can set reset equal to 0. You're not going to reset. And then this set signal, you don't really care. And these are the excitation table for 3 other popular flip-flops. The D flip-flop, which the next content is the same as the data here, regardless of the previous value here. And then the toggle flip-flop, which whenever the toggle signal is 1, the flip-flop content will be flipped. Otherwise, it remains the same. And then the JK flip-flop, which is similar to RS flip-flop. So now let's use a small example to see how we can specify sequential systems. We want to design a circuit with 1 input X and then 3 output ABCs. And the X will have 1 bit per clock cycle. When X equal to 0, the output remains no change. When X equal to 1, it's going to repeat the binary sequence 0, 1, 3, 7, 6, 4, one at a time. So what we have here is we want to draw the state transition table. So in the state transition table, what we have is we have a big column of the current state. And then we want to go from the current state to see what will be the next state. And then the next state depends on the input value. So based on different input values, your next state can be different. Like in this case, if X is 0, the state remains no change. So that is why these 2 columns, they are identical. And then when X is 1, we go from 0 to 1. We go from 1 to 3, and so on. And we can represent exactly the same information with this we call the state transition graph. In the state transition graph, we have states. And for each state, we have outgoing edges, which are the transitions. It tells you that from this state, given an input, where this next state will be, and what will be the output. So it represents exactly the same information as the state transition table.